Hello, everybody. Great to be here. Well, I shouldn't lie, because usually on Sunday afternoon, I'm at home having cake and coffee with the family. So there must be something why I'm here, and it's you, of course, yeah, to make that sure. It's also difficult to speak after Dan Stanzioni, not only because Dan already said we are both right, yeah, so what else should I say? The other thing is, Texas is also very much comparable to this free state of Bavaria. Starting from the attitude of people with exaggerations and these kinds of things, yeah? And the beer, of course, yeah? I'll get to the beer part in a second. So I'm talking about the Leibniz Supercomputing Center, and I'm also talking about the new machine, and you will see then we're just half a year in front, kind of, yeah? That's the difference, and also in the numbers we have. And I titled this talk, The Quest for High Performance Supporting Science, and I really mean this, the broad field of science, as many as possible. And the machine that we are talking about is called SuperMOOC Next Generation. So it's a series of SuperMOOC machines. You will see all of them using Intel processors, and the last one is SuperMOOC Next Generation. So when I talk about the Leibniz Supercomputing Center, it's basically these 5 buildings here in front, starting with the entrance on your right-hand side, then 2 buildings for all the employees, a lecture room building, a visualization center, and then you have this twin cube. The twin cube is actually a 5-story building plus the roof. We have about 150,000 square feet, where about 1/3 is going to computing. The rest is needed for these little things where Dan said operating is easy. Yeah? That's what we do with these 2/3. You also see on the rooftop there these little boxes, and these boxes, each of them cools about 2.2 megawatts. So at the moment we can go up to 10 megawatts, and one of the issues we have is for the next system we will have to upgrade that, and we're planning an upgrade to 30 megawatts to get there. So the interesting part is, of course, what is in there, but before going there, let me give you some examples on what Bavaria is and how it is connected to Germany. You see the Germany on the right-hand side of this slide. You have some of the big cities. The big city of Bavaria is, of course, Munich. And one of the important things is that Munich is the largest state by land size, but also in terms of the strongest state with the economic growth. So it is important for us also to have all these other partners there. And we are sometimes called the Silicon Valley of Germany, meaning there's all these infrastructure and IT companies around. Intel is not far from where our institution is. We also have these other companies there which bring in these innovation aspects, biotech, environmental tech firms. So it all comes together, and the question is, why do we need a computing center there? There's also one thing: we are an academic computing center. We are not there to sell cycles. We are just there to do academic research. And we actually do this for these 2 universities of excellence. So in any rating you go, it's always the 2 Munich universities that are leading these individual ratings. And that's also important in our case, not only because I'm a professor at one of these universities and the other board members kind of are distributed equally. This brings together a number of other things that we have there, including the headquarters of Fraunhofer Society, Max Planck Society, and also Helmholtz Association. So it is really an area where we are working together, and Max Planck Society computing and data facility is just across the street, more or less. So we are able to share some things like sharing file systems, mirroring across the street, and also we're working on joint cloud opportunities there. So it's glad to have these people around. Some of the things on this slide just explain that we have been doing this since 1962. So it's an old institution. We actually were founded when many of the universities didn't even think of, do we need a computing center? And we've now grown to about 250 employees, including people, of course, doing 24-hour cert. And on the right-hand side, you see what we are doing in terms of services. We start really being the basic service provider for the Munich universities. That means we start from the desktop. And that's an important aspect. Actually, we have a service called the Munich Network Management Machine, the PC, and that is a fully configured and remotely managed system. And we actually installed 4,600 of these around the greater area of Munich. So scientists actually, when they come in, they get one of these systems, they log in with their account, and they can immediately work. And the important part there is, you will see, when you scale that up, they can go to SuperMOOC. It's the same architecture. So from all these 4,600 and any laptop you have the same system scaling up to where you want to go. We also scale up in terms of our activities. So when things become bigger, we are a regional computer center for all the Bavarian universities. And then you mentioned you're installing systems each year. We do the same, basically. So there is about 2 million euros per system that is installed, the cluster that is coming in, different categories, different characteristics. That's what we do for the Free State of Bavaria. The third line is the Gauss Center for Supercomputing. This is together with our friends in Stuttgart and Jülich. We are the national supercomputing center for Germany. And the task there is really to provide at any point in time the highest computing performance for all of Germany, which means the systems that we are running are funded both by the federal government and the local government. And together, we try to install a system that helps any scientist in Germany. And a fraction of that system actually goes to Europe, because we think across the borders. We are collaborating with many scientists also in the other European states and, of course, worldwide. And through initiatives such as PRAISE, we are able to kind of collaborate also on these systems that are there. If we take a look at the system, we have this pyramid that you see in any of these things, and we actually start, as I said, from the desktop. So we have the desktop that goes up through things like high availability clouds, compute clouds, systems with large memories, systems for machine learning, different systems with different characteristics, and SuperMOOC is just the top of the pyramid. But we have to service everything, and we really go with one of these systems from bottom to top to support all these activities. And the portfolio that we are running is also quite diverse. As you see, we even provide the network for Munich, the research network. So the research network means we provide the connection to the 580 buildings of the two universities. This is 4,600 kilometers of cables, and this goes, for instance, up to Germany's biggest mountain, the Zugspitze. Why? Because there is a research station on top of the Zugspitze, and these scientists need to bring the data to the machines, of course. So that's part of our service. Things include things like storage, big data storage for the library, the virtual reality and visualization center where people kind of can book and use the resources there. And then, of course, at one point also the high-performance computing infrastructure for the diverse tasks they want to do with the highest available performance. Now let's take a closer look into SuperMOOC as this machine on top and the success stories we have. So if you take a look at this, what you see on this picture is SuperMOOC phase 1 and 2. It's 2 generations of SuperMOOCs already. The one in the back, occupying about 600 square meters of this room, is SuperMOOC phase 1, as you see, with 3.2 petaflops installed in 2012. 3 years later, we installed SuperMOOC phase 2 with 3.6 petaflops. It's only 2 rack rows anymore. So 3 years later, you go down with the size you need, the area you need, with the electricity you need, and you get the same performance. And you see the empty space there. This is where we put in SuperMOOC NG. So that's the area where the new machine comes in and then again increases the performance we have there. Interesting about this infrastructure is also we do a competitive dialogue for each of the procurements. So it's really a competition between the vendors. And we're not prescribing which architecture we are using. Each of these systems has actually been using Xeons in a row. So we have Xeons always winning our competitive dialogue, and the new system is again a pure Xeon system from Intel that comes in here and continues this tradition of providing the performance. Now what we did with these systems, here is one example, SISOL, a numerical simulation of seismic waves. And that's one of the things where we were also going to what was it called? The finalist for the Gordon Bell Award was one of these things. Why? Because we were able to get 1.4 petaflops from the 3 petaflop machine, meaning we were able to get 44.5% of peak performance for production runs. So this is a software package developed in Munich that is actually running on a regular basis for production runs, and that actually achieves almost 50% of the peak performance with a production code. And that is really optimized for the architecture that we have there, and it's an interesting application of why we need these systems. Another example is actually, what if we would combine both of these systems? So we were combining all the supercomputers that were there, and my friend Peter Coveney came to me and said, we would have a code that would fit on both of these systems. So we were doing actually molecular simulation, trying some docking experiments for personalized medicine, and we just said, we'll give them whatever is there in the room. So basically, after maintenance Friday afternoon, we said, you know, we're not bringing the machine back into user mode. We give it to him. You can have it until Monday morning, and you can use it as much as you want. And they were actually doing 8.9 million core hours over the weekend. They produced 5 terabytes on data. Monday morning, people came back to the office and said, we're shutting back the machine, turned off this application, and then moved the other users in. And we didn't actually know what was happening. We had to wait until lunchtime. And at lunchtime, Peter called me for the first time, and he said, you know, this is fantastic. We never had the possibility to run that much on such a system, and we were able to see some new scientific phenomena on the system. That's why we are doing it, actually. That's why we want to have these systems. And in this case, we actually got payment from Peter. He brought this bottle of champagne. And that's different to many of the other application users who just cite us in their papers, yeah? It was not that bad. Good. So that's another example. Now, here is one thing that you also see. This is a simulation, a video that came out as a byproduct of Peter's work. It's actually a simulation of the circle of Willis, part of your arterial tree. It's from a concrete patient, and we're actually simulating the blood flow in there. So the idea is really with personalized medicine, we go in this direction. We don't do it on medical treatment on heuristics. We do it on the particular patient. And we had to do these few seconds that you see here, consume a number of thousands of cores for a number of hours just to produce what you're seeing here. Because we want to be as close to the physical phenomena that we are observing, and it was an interesting aspect to do that. Now, another example is on the next slide. What you see here is astrophysics, and of course, thanks Dan for putting that in your slide as well. So we're trying also to scale up astrophysics, and Munich is very well known for the big accumulation of astrophysics people we have there, and we were actually doing a number of projects with them, and what you see here is the fractions of the computation that we can do. We actually have a user interface where they go in and say, we choose one of these areas, and then we go in there and do a simulation for the small part. And the astrophysics guys are really cool guys because they help us all. They always need more. So they tell me that right now they are able to simulate about 10% of the visible universe. That means with the next machine, they might be going up to 20%, yeah? That means we need to have some more machines in the future because they possibly want to simulate whatever is there. And that's a good example that we have there. It's one of the examples where also in Munich we see the acceleration. And on the curve below, you also see that with every machine, so the blue lines give you the 2 old machine, the orange line, the latest version with phase 2, and you always see how this scales up. So we're really kind of pushing the frontier forward, and then kind of getting to an area where we want to. Now, the next slide I had in there then, and since I knew you were in front of me, was about disaster management, these kinds of things. So I killed that and instead said, what if we look below our continents, below the Earth, inside the Earth's mantle? And this is an application that is also interesting, because in this application, Peter Bunge from the University of Munich is actually putting together a model of why the tectonic plates are moving, and it is a model that plays with the densities and the temperatures in the Earth's mantle. Now, the model looks not that difficult here. Actually, the results of the simulation here and what we are visualizing is 37 terabytes of data. Now, you need to want to put these 37 terabytes on data on your GPU and visualize it, then you need certain techniques. You need the network, you need everything to transport it in. Actually, Peter and I were sitting at an Italian restaurant, and we were discussing, what funny project could we do? And he said, how about using this data and performing a flight into the inner parts of the Earth? And I thought, we have to move these 37 terabytes around, It's not that easy. I said, yeah, but we need some challenges. And we can do that. We actually showed that at the Ars Electronica Festival in Linz in Austria this year, and people were basically flying with us on a tour inside the world, and that was a really interesting project that we have here. And you could actually see that even on this part, on this continent, because the American Natural History Museum from New York came to us and said, this is an interesting model. We would like to showcase that in New York. So there is a place where you can see the model in New York. They actually took the model and made a 3D print. So you can really also touch it in a sense, which is, I think, an interesting application. Now, why did I talk about these applications? Because these applications are some examples of what we are doing. And as you see here, the goal that we have is really to support the wide array of different applications from all different domains. Of course, there are some heavyweights in there. Computational fluid dynamics on our system is about 1/3 of the applications that we are running. Physics, with some particular examples that you see here, is about another third. But the third, so to say, is about all these other applications. And we really don't want to limit people coming there as long as the applications scale up and make efficient use of these applications. So what we are also doing, we are collecting statistics. And these statistics are in a book. So what you see here is the title page of that book. And I'm sure, do we have copies of the book at our booth? So we have copies there. So if you're interested, it's an interesting book because it has about 200 pages. And each application has only 2 pages in there. So each of these 100 applications there show concrete applications on how to use these systems. And you see the numbers up there. So with SuperMOOC alone, we spend about 7.6 billion compute hours in about 5.6 million jobs by 750 different research projects. So it's really this width that is special for our project. It's not only a handful of applications, but it's very many of these different applications that we want to use on our system. And you also see it's about 2,000 researchers who make use of that. And the idea is really, you go there, you work on your model. If it fits on your laptop, fine. If you can scale it up to your local cluster, fine. If you need a bigger cluster, you come to LSC because we're providing this on a Bavarian level. And if it exceeds what you can do on this level, you need to go to the next kind of system. So next kind of system brings me to actually SuperMOOC Next Generation. So what is so special about it? What you see here is a nice picture of the room. So the room has 1,200 square meters. And SuperMOOC NG is only the part with the green fiber optics cables. So the other ones is in the background, but it looks nicer if you see it from this perspective. We have another picture here where you see it from the front. This is the setup that we have here. And the interesting part about SuperMOOC NG is it's 100% Xeon cores. So there is no accelerator, no GPU in that sense in the system. We're doing this with pure Xeon. And why are we doing this with pure Xeon? Remember the application mix that I've shown you. When we procure this system, we take these applications as the measurement. So what we do is we take some of the representative codes, we make small benchmarks, small kind of kernels out of what we're actually running. We distribute them with their weight, and then each of the vendors has to compete to get the best performance. And in the end, that's why Intel, as prime on this project, was winning the project, because the Xeons provide the best performance for the application mix at that particular point in time. And that's an interesting aspect, because it allows us really to go from the desktop to the highest performance computing machine with the same architecture and with all these things. And actually, on the next picture, you see our Prime Minister here. He was visiting us, so he's very IT interested in a sense. He said, could we just start the machine before the election kind of things, yeah? Now that was just pure coincidence, of course. I was making a joke here. Now the important part here is, and we were discussing that, and I was just saying to Jack Dongara before the meeting, we're not targeting to be the first on the top 500 list, but we have the goal to be the best machine in terms. So we want to machine that, and Dan has already said that for his particular environment, we want a system that actually fits to what the users need. So in terms of characteristics, what we have here is we get about 26.7 petaflops. Actually, we can even go up to 30 petaflops depending on how many watts we put into the system. We have 720 terabytes main memory, 70 petabyte disk storage, all directly connected. And as I said, we have Skylake processors in there. Now, not all this system is comprised of islands, and the islands are different. So the memory is not the same on each of the nodes, because we also see from the characteristic that some of the applications need much more memory, and that also, of course, goes back to when we talk AI, machine learning, these kinds of things. Now, in total, we have about 311,000 compute cores, and I'm not going to spoil the result, what we have with HPL, because we will see that tomorrow in the news probably. So that's one of the points where we come in, but that's a thing that we are looking forward to. Now, the system is also special in a way because we use direct warm water cooling. And cooling, you showed the equipment that you have at TEC. Now, the idea that we are having is we go in with warm water. And the water, I was just looking it up, is 40 degrees Celsius. That goes up to 104 degrees Fahrenheit, which is an interesting number. We're cooling the system with water that can be up to 104 degrees Fahrenheit. We go in there, of course, it comes out on the other side with even more heat. And then the question is, what are we doing with all this heat? Now, since it's a bit cold in here, I think we could have some heat here in the room from SuperMOOC. It's a bit difficult to transport, but we're actually heating our building with the waste heat from SuperMOOC. We're actually able to heat other buildings as well, and as new buildings are coming to campus, we're actually putting the appropriate infrastructure in there. Now, for the heating, we need at the moment less than 1% of the waste heat. So the question is, what do we do with the rest, with the 99% of waste heat that's still there? And some of the people working in this are sitting in the second row. We're very happy on some of the ideas, because what we do is we use adsorption chilling. This adsorption chilling allows us to use the waste heat to produce cold water. Actually, when you remember the picture with the two SuperMOOCs, the waste heat from SuperMOOC phase 2 produces enough cold water to cool the old systems where we still need chilled water. And that's an interesting aspect. We put that together. Now, I'll come to that back in a second. Let me just conclude the last paragraph on that slide. One of the things, and Dan was also mentioning, is the convergence of clouds and HPC. We have actually done a different approach here, because what we did is we put the cloud in front of the HPC system. The idea is really that you kind of configure your virtual machine, you set it up as you want it, and when you come back next time, it's your virtual machine, it's your setup, and you just continue what you want to do. In this cloud in the front end, we also have GPUs in there. They are there for pre- and post-processing. So you really have on one end the high capacity, the high capability simulation engine, and in front of them, you have the cloud to do all these other things that you need to do when you want to do science. So that puts all these things together, and that's the architecture. Now let me come back a little bit to the energy efficiency. Actually, when we talk energy efficiency, it's not only about what we have in the system. It's basically everything around the data center. We start not only with the HPC system software and system hardware, but we also consider the infrastructure, as you have seen, the building infrastructure, and also the HPC applications in there. So when we start an application on SuperMOOC, the application actually tries to use just the energy it needs to complete in time. So it's energy to solution, and it's not kind of use all the energy that is there. The trouble is, of course, we have with a very varying energy consumption, but the idea is that we are always using just as much energy as we need for the system, and we have optimization strategies for the entire infrastructure, kind of. So what we do is we do direct liquid hot water cooling, and I think we were the first ones with SuperMOOC to do it on that scale. We do heat reuse, as I said, with heating and adsorption chillers. We do energy-aware scheduling. We also have, and that's what Michael and Daniele are doing, is we have all these sensors in there which just want to understand these things. So we have one person actually at the center dedicated to understanding what the building is doing when the system is simulating, because we need to understand how that fits together. And then in the end, we have a database that actually gives us in high resolution all the statistics that we get there. And we at this point in time, we are at the level where we can kind of, within a 15-minute interval, change the power provisioning from the energy provider. So basically, when we see a job coming up in 15 minutes that need 20% more power, we could just buy some more power for these things. On the other hand, if we see the jobs kind of going down, we could kind of decrease the power consumption and then again kind of save some of the money. The idea with this one is simple. We don't need to generate any revenue. It's not about generating revenue, it's about doing science. So whatever we save with energy efficiency is money that we can spend on science. And actually, with all these things that you see on this slide, we're able, with just the 2 old SuperMOOCs, to save 2 million euros per year. And that means 2 million euros more on science and research. That's why we're doing these things. Now let me come to a little bit of an outlook of how that fits together. You've seen the acronyms of CoolMOOC before, and this picture actually explains how that fits together. So we have the production system SuperMOOC phase 1 and phase 2 on the lower part of this slide here, and on the upper part you see the CoolMOOC series. Now CoolMOOC is our playing field, kind of. With CoolMOOC we try new things, we go in there and we try to kind of again push the limits of what we can do. You see in terms of the incoming water that we have there, you also see different technologies. So what we do is we're basically installing smaller versions of clusters where we try new things with energy consumption, and this actually gets us a number of awards. So just this year, we were able to get an award for SuperMOOC for the adsorption chilling and one for CoolMOOC 3 for actually the hot water cooling that we have here. So you see CoolMOOC 3 on this particular slide here, and these 3 cabinets on the left part of this system are 100% hot water cooled. They're also kind of containing all the heat, so that they are thermally isolated, so none of the heat goes to the room. So all we do here is basically we're cooling not only the processors, the memories, and the chips in there, we're also cooling, for instance, the power supplies. So what we tried there is basically we tried together with our partner Megware on this, we tried to build power supplies that are inside a metal cage, and the metal cage is actually using the warm water to cool the power supplies. And that all fits together. And that is actually one thing, and I brought this especially for our friends at Intel, because we want to do that with the next system. So that's the challenge for you, kind of. Yeah? So if you put that all together, it's clear that with the 3 systems on top and the 2 production systems, what we wanted to do with SuperMOOC NG is basically put that in there. And with the adsorption chillers that we have here, we're also kind of going into that way that we say we can produce at this point in time much more chilled water than we actually need. So the question is what we're doing with this chilled water, and we are kind of exploring some ways of putting storage in there so that any of the research institute on campus could have free chilled water from the waste heat that we are doing with our system. Now SuperMOOC NG is formally phase 1, so there must be phase 2. But of course, we are also talking into the future. So with SuperMOOC phase 1 being installed now, we are thinking about where we're going to. And one of the things is, of course, big data, and I'm giving you some examples on what we do there. And when I say big data, I actually mean big data and all these AI things, whatever hype name you want to use. And that together kind of comes to a system where we, again, starting from the applications that we have and the needs from the application users, then together with all the things that we have on scaling, energy efficiency that I meant, I didn't talk about the unified storage in the end. So the idea is really that basically all the storage we have is the backbone, and the system connect from the front. And what we're doing there is basically having one of these unified data storages where you can use the data across the systems and also integrate it with a metadata system, research data management that fits together. Now I want to give you some of the examples that are happening. One is in our role as Big Data Competence Center, again, for the state of Bavaria. And the example here is that we have all these different components here, different systems that play together. And what we want to do is we want to use the outcome of the simulation, like what we see here, and then see how we can use all these other things in the workflow. So when I talk about AI, machine learning, deep learning, it's always a component in the workflow that we are observing. So what we want to do is this example here, for instance. We have here a group of scientists who did 7,500 years of climate ensembles. So what they did is kind of the influence on climate, on society, and all the other aspects. And they produced some 400 terabytes of data for these things. And then that was their research projects. They were done. Then came around a young scientist. She saw this data and said, you know, with all these data around, could we do something useful with it? Could we detect some dead patterns? So what she did is she took the simulation data that was coming from SuperMOOC and then trained a neural network to see if there are some characteristic patterns in there. And that actually delivered some of the results what we see here, and that's called the 5B weather conditions. And that means these are extreme weather conditions where you have flooding on all these kinds of things. And these flooding conditions can even from the climate data pinpoint on the exact dates. So in these 7,500 years of climate, you see extreme weather situations that have led to floodings and other aspects. And that's an interesting point. So it's two different things, just reusing the data and then integrating it. So when we talk about future systems, one of the things is how we put this together. Now here's another example. What you see here is the city of Berlin with the Tiergarten in the center. And what you see also these different buildings, and you see different colors on the buildings. That's actually the satellite data that we are getting at this point in time. And we're talking about satellite data, about 60 petabytes per year that are coming in and that people can use. And our colleague, Professor Chu, is using that with her particular, that was the wrong button, with her particular data, and she was taking a look at the deformations of buildings. So what we see here is actually Berlin's main railway stations, and what we see is from the observational data from the satellite, we see how the building is expanding over time and which part of the structure are actually affected by the weather on the ground. And in order to do that, you need to move around large amounts of data. So Professor Chu came to me and said, you know, I have these 4 petabytes of data lying around. Could you help me with that? So that's the challenges of today. We're not talking gigabytes or terabytes. We're talking about petabytes that people want to analyze, people want to kind of move around and use in their systems. So if we put this all together, when we talk about the future system, the future SuperMOOC, or whatever you call it, we called it ExaMOOC. Strange. You can guess why it's called ExaMOOC. And of course, we have some estimates. So we're working on the assumption that this system will be up to somewhere 25 megawatts. We already have the discussion. We know that we can bring this to the building. We know that we could host the system in the building. So there's some preparation going on there. And this system would include specialized islands to do the other things. So when I talk about AI, I believe that in the future we will have an island in our HPC system that actually kind of includes that particular aspect and that allows us to simulate that. And to talk about that, all the hype with AI, and I'm sorry for being frank here, AI depends on the data. Now, if we talk about all these data, it also means that somebody needs to produce the data. So that's what we see. We see that machines like SuperMOOC NG are producing the data, and once the data is produced, you put it into your AI system, and then you do all these other things. So I had already this picture. You remember Jurassic Park? You remember the little raptor that was kind of following the people? And for me, the AI is the little raptor, you know? But the problem is there's the T-Rex around the corner, and the T-Rex is the supercomputer. And actually, there's this one scene where the T-Rex captures the little raptor and then makes sure that something's going on there. And that's kind of the comparison. So we should put this in the right relation. We should put this together. And I think that's the planning that we have at this particular point in time. We need to find out how that works together. And of course, we also have this other task. Bavaria also wants to have a quantum computer, of course, which we need to see how that fits in. Bavaria also has a space program, yeah? So there's a number of things that are going on. But now I'm back to the point where Bavaria is very similar to what we see in Texas, no? So putting that all to an end, basically, what I believe, and I hope I was able to show you, we have these scientific, this wide range, this broad range of applications which are there. And these applications kind of are not a handful of applications. It's really that you don't know where the next scientist is coming with his data or her data and who wants to use that. And we wanted to have a system that really supports that. The advantage of doing that in Germany is also with our partners in Jülich and Stuttgart, we have different architectures. So we can really focus on these different areas. Our task is really to make sure that we have this wide array of different applications and to provide supercomputing as an excellent tool. And I think we have a good choice with the architecture that we are using. Now, there is, of course, also a part of the competition in there. And as I said, I don't want to be number one on the top 500 list. I'm just happy if my users are happy and say we have the best system for their particular needs. And of course, we do energy efficiency. And I mentioned energy efficiency as one aspect where we're not doing this to make sure that the life for our users is difficult. Yeah? In fact, what I would want to do is I don't want to give away cycles on a basis that they just get cycles per hour. I would love to give away cycles on an energy basis, meaning if the users are able to save some energy with their computation, they could do more computation, because that's what we do there. We are doing energy efficiency because it saves money. It generates money that we can put into science and research. That's why we are doing it, and that's why it's important what you two guys are doing there. Yeah? So continue to do that and save some money for science in that sense. Now, to conclude, I have two more things. Number one is you can have a little copy of SuperMOOC NG. Now, actually, it's not a real one. It's a virtual one, so augmented reality, this stuff. So if you take one of these paper versions, you can actually hold your mobile phone, your smartphone, and then you see SuperMOOC inside the building on this particular sheet. And in order to get that, actually, I would recommend you come by and visit us. This is the Bavarian booth. It's actually about bits, bytes, beer, and Brezel. And there's everything there, bits, bytes, beer, and Brezel. Come visit us, have a look at what we do in Bavaria, and thank you for your attention.
Well, thank you, Dieter, for that stimulating talk. I got a couple of questions here. Given that LRZ is one of the 3 national centers in Germany, and its mission is to provide the highest capability in terms of computing to a wide range of different applications in Germany as well as in Europe, what is driving the move of AI workloads onto the HPC infrastructure?
So it's actually the needs from the users. It's when you do science, AI is a component. It's part of your workflow, and that's kind of why we see a change in the future architecture, as I've explained with ExaMOOC. Yeah. So the idea is really that I don't see this discoupled. You have the T-Rex producing the data, and the Raptor then taking care of that with that example.
Okay. You mentioned key HPC and AI workloads that are planned for SuperMUC next generation. What scientific discoveries should the German and European ecosystems expect to see coming from LRZ's new system?
Well, that's an interesting question. If I would know what the next scientific discoveries would be, point is, I'm not judged on the scientific discoveries that are coming out. I'm judged on the system that is provided to the users to do their daily work. And if I would say we don't need a metric on flops or something, we need the metric happy users.
I see.
And if we are number one on the happy users metric,
you're good.
That's my goal. And then I don't care which scientific discoveries it actually is.
You want to be number one on that list.
That's
okay.
my goal, yeah.
Okay, very good. Thank you so much, Dieter.
Thank you.